Hello, welcome to the Tech Behind the Magic. Today I'm going to be talking about how SORA works. So this is actually the first in a series of videos I'm going to be making, talking about really amazing technologies and inventions over time, and exploring their history as well as the technology that powers them, and diving and just enough into the technical details by making it really easy to understand for everyone. I'm John Alafenwa. I'm an AI scientist, and I'm really excited about all the incredible innovations happening in the AI space. And yeah, just really excited to take you through the history of like how we've evolved from like deepfakes years ago to like Sora today, which I think is a really amazing technology. So first of all, this is a video generation from Sora. This is a very short glimpse of what Sora can do. But of course, later in this video, we're going to see like a lot more amazing things that Sora can do. And this is just like a cloud with like the word Sora written on it. So before we get started, let's take a look at 1 year ago, sort of, and see this, famous Will Smith video and Will Smith eating spaghetti, and this was like a really funny one, and just kind of highlighting how much the technology has progressed. And now I'm going to be showcasing this video which I made to demonstrate like how the technology has evolved. All the way from like the very early image generation models to Sora that we have today, and just every single thing in this video, audio, images, and rest are like AI generated. And I'm just going to play this and please enjoy this incredible history. So that's like incredibly amazing. Seeing just the journey, from like starting with the GAN images, you show like really low resolution, low quality images, some of them like grayscale initially, to like evolve into, this like really interesting, uh, you know, images that were used for like deepfakes back then, like Saigon and rest, and then evolving to like Midjourney, Stable Diffusion, and finally to this really, really incredible and mind-blowing level that we have with Sora today. And you can see that rich history and all the innovations along the way and how much, of a massive jump that we've had. And so now we're going to be talking about the journey to Sora, like what technology led us there, like what are the technology choices and discoveries that we as a AI community, as a world, right, as planet Earth really, kind of like went through to get to this space. So I like to think about this as a couple of generations, and I think the first generation was like 2014 to 2021 with generative adversarial networks. And so GANs were like infamously used to create deepfakes. I think that was probably the most popular application of them. And that wasn't great, right? But they were trained with, through this system of like having two AI models compete with one another, where we have one AI model trying to like generate this like interesting images, and then we had another AI model trying to like detect which one was like real or fake. And through this kind of like adversarial competitive process, we end up with a model that's actually like generates like very realistic like pictures of faces or whatever else we want to generate. Now the images they generated were like really cool, but they were like really, really hard to train. As back in 2018, I spent some time training GANs, and they were like really, really hard to train because it was just like hard to control them. Even like after training them, it wasn't always easy to like get really good images out of them. Many of the images you see that were like really cool are like cherry picked, and they because of their unreliability and kind of like being brittle, it wasn't really useful for much practical purposes, which is the reason why, some of the only like major popular uses of them that we had about was like, deepfakes back then. But of course, today we are used to like, image generation models being used for a lot of practical uses. So the second generation was like image diffusion models, which, replaced GANs effectively. Um, they at this class of models called diffusion models power and all the state of the art models like DALI, like Stable Diffusion, like Midjourney. And they are like really, really cool. They generate images through this kind of iterative, sort of like a for loop process called diffusion. And so it's like the model generates the images step by step using like a for loop, and the then depending on the number of steps that we throw at it, it gets better and better. And they are like quite easier to train compared to like GANs. They are like very stable, and also they work reliably, right? Like while if when you prompt a diffusion model like Midjourney, it might not always give you exactly what you want, but it will always give you something like really close and sensible, which was like different. So, like GANs could just give you like complete like rubbish, right? If you don't like really control it really well. And then the diffusion models, of course, generate images of unprecedented quality, which is like way, way ahead of, the GAN generation. So that was like for images, right? And yeah, all the images you see here are generated across like DALI, Midjourney, and like Stable Diffusion. And they're like really cool, very futuristic images. So the final generation of these, at least right now, is like video diffusion models. And they really started off strongly in like 2023 is when I like to think that they started off in a meaningful way. And on the left, we have, I think, Google Lumia, and then on the right, we've got Sora, of course, which is, always like really interesting to see. And video diffusion models, they generate high quality videos from text through the same like iterative process of diffusion. So it's basically the same technology powering image generation, but like with some modifications that allows it to work really well on videos. And modern diffusion models such as SORA are based on transformers, which is the same class of neural networks that power GPTs and large language models of all sorts. So unlike previous image diffusion models were based on like convolutional neural networks, which is kind of like a previous generation of like models, and like but models like SORA are based on transformers, which makes them a lot more interesting. And they can generate temporarily consistent high quality videos. That's videos where we have consistency across every single frame. As you can see, like here we could see the horses, you could see the buildings, and they are consistent both in terms of 3D, their position, and how they move across the time in the video. But of course, they are like really, really expensive to train, unlike like image diffusion models, even though they are like, I guess, kind of easy to train in some sense, more straightforward than like say GANs, but they are very expensive and costly, which is why only the biggest organizations can do that right now. But hopefully, the cost will go down eventually. And moving further, let's think about how the diffusion models work. So we've had this whole history, right? Of like we started from GANs, went to image diffusion, and now we have been doing video diffusion. But of course, one thing that stands out really across like the modern stack is diffusion models. So let's take a step back and think about how diffusion models work and then see how they apply to images and of course like to videos. So the way to think about a diffusion model is to think about, drawing on a blank canvas, right? Artists draw on a blank canvas is, start from a blank canvas and gradually adds details and details and details until you have a perfect, artwork or painting or whatever you're trying to like create. And diffusion models sort of work in the same way of like they start from a blank canvas and they gradually through like a number of steps, which could be like 1,000 steps or 500 steps or whatever, they add like more and more detail to images as they go, and we'll see shortly how that works and why I kind of compared it to this concept of like drawing on a canvas. First of all, let's look at the process of like generating a picture of a car via a diffusion model. So what the diffusion model receives initially is like a random noise, which is created, through like Gaussian noise or some sort of like probability distribution that creates a noise. That's not like a complete noise. So we can think about the noise on this left side as like our blank canvas. It's just noise. There's no real detail in it. And then we pass that into a model, and the model is then trying to produce like a less noisy version of that with some detail added. And we pass the output from that to the model again to produce another less noisy version. And we're starting to see the shape of the car, and the details in the image like really appear as we do that more. And we take the output from that, pass that again to the model to produce like another less noisy version, which is kind of like we are gradually painting the canvas, right? We are like adding more and more detail. And we do this until the very end where we have this, perfect image. That's exactly what we want. So we go from like complete noise, just random noise, no detail, through like a for loop of passing that to the model and taking the output of the model and passing it back in. We are gradually like painting that canvas until we like end up with like going from noise through a set of steps into like actually a perfect image which represents what we want. And looking at this from like an architectural perspective, we can think about on the left side here, we've got like, that blank canvas with no detail in it. And then we have a text description that says Tesla car on the road, right? That's like what we want to generate. We want to generate the picture of a Tesla car on the road. And we take that blank canvas plus that text description, feed that into the diffusion model, and the diffusion model will produce a new, image that has some tiny details in it, like add some details to it, but not like perfect yet. So we take that output plus the text description again, feed that to the diffusion model again, and it produces another version that has some more detail in it. We take that plus the text description, we feed that, we continue that loop until the very end where we have, this image and this text description. Feed that into the diffusion model again to give us that perfect image of a Tesla car on the road through just this for loop process of taking a blank canvas, passing it into the model. It produces an output, and then we take that output and we feed that again to the model till we get to like a fixed number of steps, which could be fixed like 50 steps or 100 steps. So number of steps is fixed, right? It's not like it could be like 1,000 steps, whatever we fixed it to. And the more the number of steps, the more computationally expensive the process is. And one of the things to note is that the blank canvas we supply will be of the same resolution as the final image. So if you want to generate a 512 by 512 pixel image, then you create this random noise of a size 512 by 512, and that's what you essentially paint on till the very end. And let's now take a look at SORA. Like how this is, by the way, so this whole diffusion process is how Midjourney works, is how DALL-E works, is how Stable Diffusion and basically any like image generation of modern times works today. And then the idea is then we want to take this and apply it to video. So let's see how, SORA does that, how SORA takes this diffusion process and extend it to like video generation. Now, but before we talk about the technical bits, we can talk about the capabilities, right? And talk about like how it actually does that in terms of like what are the capabilities that it can do on this whole taking a blank canvas and like doing something cool with it. First of all, SORA, unlike just diffusion models for image, can actually generate video, right? In this case, I'm gonna play this, which is an old man taking a pleasant stroll in Johannesburg, South Africa during a colorful festival. Like, so this is like really cool. You could see, all the incredible detail in there, which is like, just typical SORA. Now let's go further. In this, one of the cool things that SORA can do besides just text to video is actually taking an image and generating a video from it. So in this case, we've got this image below, and then we have a prompt, text prompt that's like added to that video, which says, in an ornate historical hall, a massive tidal wave peaks and begins to crash to surface, seizing the moment, skillfully navigate the face of the wave. So we take this text plus this image, feed it into SORA, and this is what SORA does, right? SORA, based on the text, it animates the image for us, which I think like is like really, really cool. And you can think about being able to just take any picture, right? And a text description after 90 video, which is just like incredible. So one of the most amazing applications of SORA is being able to edit a video. So on the left here, we've got a video, and on the right, we've got, we say change the settings to cyberpunk, which is like take this video and change the settings to cyberpunk. And when I play that, you can see how on the left we have the source video, on the right we have the SORA generated video, and it's able to like recreate the exact environment, the objects, while changing the settings to be cyberpunk. And I think this is like one of the most incredible and amazing things that SORA can do. And for something like filmmaking, you can think about just being able to record a movie in New York, and then being able to just change the setting to be in the Sahara Desert or something like so completely different, right? And this means you can basically like do anything you want to do with a video by just textually describing the edits you want, and this can save a lot of time in video editing processes. And it was really incredible to see what SORA can do, and really I'm actually looking forward to see all the amazing things people are going to do with it when OpenAI eventually releases it, hopefully sometime this year. And yeah, so these are the core capabilities of SORA, going from text to video, text plus image to video, and then text plus video to video, which is like crazy. Now let's take a step back and think about our SORA trained. Now the first step is the training data. Now one thing to always keep in mind with all of these crazy models is while the architecture might look cool, that's like the way the diffusion process works and transformers, all that, the single most important factor is the training data. Like very good, high quality training data, is key to any of these algorithms working really well. On their own, they can't really do much without like having good data. And I think what these new algorithms are good at, transformers, diffusion models, is like they can make the best out of the data that you give them. So for SORA, and all these details is from the SORA technical report, the OpenAI took lots and lots of internet videos, plus video, description, like, videos with like their description or caption. And then, this is separated sort of like, well, we got raw videos, which are of variable resolution. Some videos are like low resolution, some high resolution, like of different like aspect ratios and whatever. Uh, and like one of the interesting things about Sora is that it can generate like different resolutions of videos because it was trained like different resolutions of videos. So we got like the raw videos and then the raw descriptions slash caption. Now, one of the things to note here is that when you're taking like internet scale videos and their captions, the captions won't be always as sensible as like the kind of prompts you want to give to the model. So like you can find a YouTube video and the description and the caption might not really be the kind of prompts you will write if you wanted to generate that video. So how to solve this problem is like OpenAI essentially recaptioned the raw captions, right? By taking the raw captions, feeding into the caption model. So this is like, hey, here's a YouTube video and I've taken a text description, the text caption of that video, the raw caption as it was written, and you could feed that into say like ChatGPT and tell ChatGPT to rewrite it in a way by which it will feel like a person wrote a prompt to generate that video, sort of like that. And so what this gives us out is like we take those raw captions and we turn them into more descriptive, more clean of caption that's kind of more representative of like how people will write prompts. And so we are then left with like lots of raw videos and very good and nice captions that really represent what people will write if they wanted to generate that video. So this is like, a really, really important part of why SORA works. And this whole idea of recaptioning, I think, was first introduced in DALI 3. And it's that same idea that's kind of like been extended to SORA. Now, so after doing all this, now if the first phase of SORA's training is what we call this video autoencoder, and this is like really important. A lot of people talk about SORA, just be like this thing that predicts pixels, but that's not true at all because SORA's prediction doesn't happen in pixel space, as we'll see. I will explain shortly. It actually happens in a latent space. So let's look at what does that even mean. So basically, we take like this video of a butterfly, and this is like, category. A video is just a stack of frames, right? Like a video is actually made up of lots of images moving at high speed. So we have like this grid of like images, which is a video here. I'll pass that video over to a video encoder model. So this is a neural network. So pass that to a neural network, and that neural network converts those raw pixels into a lower dimensional space, also called like a latent space, where the video is compressed spatially. That's like the width and height is like reduced, like converted to a lower dimension. This is, you can think about it more like when you're like zipping a file, but of course this is like a lot more complex than like zipping or any other form of like JPEG compression, whatever. So this is like this converts the raw video to a lower dimensional space where it's compressed both spatially, width and height, and also time-wise, like across video frames, is also compressed. Now what this does is we're able to go from like pixel space into a latent space that represents concept and motion rather than just pixel numbers. So we're going from like, hey, here's just a bunch of like pixel numbers that, is the video, into converting that to a more meaningful lower dimensional space where the video is now represented by concepts, by motion. So it then becomes a sequence of concepts and motion across the video. And so this is like a much more meaningful space to work in, because in that space, rather than just like represent the video with like pixels, we can represent it with things like movement, with things like 3D properties, with things like objects, and all of that is like defined implicitly in that latent space. And that is the way this is trained. Is like we go from that video to that latent space and then take that latent space and decode it back with another neural network to convert it to pixel space. So we can pass a video in there, it gets compressed to a lower dimensional space, and it can also then be decoded back into the normal raw video. So that's basically how it's trained. And during training, what we do is to minimize, like the reconstruction, ensure that whenever we feed in the video in our compress that lower dimensional space, we can always, when we now pass that to the decoder that reconstruct that to the video still remains the same and unchanged. So that's basically how that is trained, right? It's just like minimizing the distance between this reconstructed one and the original one, while allowing this latent space learn all kind of crazy things it wants to learn. Now, once we've done that, we then do this diffusion training. But rather than having like denoising image from a blank canvas, what we denoise is the latent space. So which is really interesting. So the SORA's prediction happens in latent space rather than pixel space. So we take this grid, this lower dimensional grid, we flatten it into like a 1D sequence, turn it into like a, like tokens, and then pass that flattened grid, this, which has been flattened here, plus text description like a butterfly flying, and then pass those two into a diffusion transformer. Now, so this transformer model, which is the diffusion model here, is then going to produce a new denoised latent space. So we're starting with like a random latent space, just like starting from a blank canvas or random noise in the case of like the way image was. But this time around, we have this latent space instead, initialized randomly, plus the text description, and then we'll produce a more meaningful latent space. Now we take that plus the text again and produce another latent space, and we go through the same number of steps as we would go through like for like image generation, right? And what we end up with is a latent space guided by this text description that compactly represents the video we want to produce. So basically this can seem a little bit confusing, but it's like rather than like diffusing and painting in the space of pixel, we are painting in the space of the concepts, generating and doing diffusion in the space of concepts and generating like a more meaningful version of that latent space. And so once we've produced the final version of it, we then construct that into a grid and pass that to the video decoder model, which is this one. And we get our final video as output. So that's one of the most interesting aspects of SORA, is just this fact that it actually learns in an implicit space, and it's kind of like unbounded by just the limitations of pixels, which I think is one of the reasons why SORA is capable of doing a lot of things that people never thought diffusion models and transformers could do. So this is how it works technically, and you could read more about this in the OpenAI technical report, and there's also another like review paper I'm going to link in the video. And so we go from like this let me step back a bit. This will denoising from random noise to image, with this diffusion architecture, that takes a random noise and converts that to image. And we go all the way to this process, which takes a latent space, this latent space length here, a random version of it, and then denoises in the same way, and then converts the final output to a video. This is called latent diffusion, and the idea behind this, I think, was first like popularly used in stable diffusion, right? So the final training is like this, right? We have like this video, we pass that into the video encoder model, it gets converted to latent space, and then we flatten that latent space, we pass that into diffusion transformer through a number of series of steps, like diffusion steps, it could be 50 steps, 100 steps, a loop, and then the final output is this, and then which is the predicted latent space, and we reconstruct that back into the grid, and then pass that to the video decoder model, which is then converted into raw pixel videos. So which is quite a very interesting architecture that's I'm sure is going to evolve more and more over time. So that's how SORA was trained, and this is like a really expensive process because of videos can be like really expensive, but the whole conversion to latent space kind of makes that process more computationally tractable and kind of cheaper to train. So compared to like if the prediction was just done in video space. And of course, doing it in latent space enables us to like predict and learn things like motion rather than just like pixel values. So let's think about some of the key advancements that SORA really unleashed. First of all, unlike previous models, SORA is capable of variable video resolution, any width and height and any time. So, right. So, for example, this is SORA on the left trained with fixed video resolution, and you can see some of the challenges that it introduces. But by being trained on dynamic resolution, is able to like actually generate videos that are more sensible. And this was like a really, really innovative thing because most models just have a fixed resolution that they generate and like they can't that creates a lot of problems as we can see here. Next up is like consistency across the entire video. Now this is a video generated again from Sora, and you can see as this bird is like biting, taking a chunk of this burger, and you can see how the part of it that it bit off is represented right there. I'm gonna play this again. Just take a second look at it and see just how crazy it is. This video feels like very real. And like the part that it bites off is just right there on the book, and it's just such consistency across the entire video that's like amazing. Another is like 3D consistency. If you look at this video, you can see how the three-dimensional view of that world from the top to below is maintained consistently across the entire video. And this is like really, really incredible that, just purely from this prediction in like a diffusion in like latent space enables actually learning to do 3D in a very, very reliable way without actually any physics engine, any explicit encoding of like 3D structures in there. So Sora is like really incredible, and one of the I think the most amazing things about it is this ability to scale by compute. So here is like Sora with like base compute, and on the right we have like 4x compute, and on the utmost right we have like 32x to compute. And you can see how the quality, the consistency, the 3D, everything all scales jointly as the compute increases. And you can think about how with more and more increasing compute, I think it's going to be like really interesting how much better these models are going to become, which is like the reason why like work on like better compute, more efficiency is like really important now. So these are some of the incredible things that Sora can do, and some of the new frontiers that it's opened up. And let's think about finally what's the impact of this on the society and everyone really. One of the most important things I think is that it gives us ability to paint our thoughts in video, right? Throughout history, communication has been one of the most important things that we humans have strived to do, from like, drawing, and like, even like cavemen, like to like, carve out like stuffs inside on like walls, on like on rocks. We've gone from there all the way to like painting and using computers to like write, to like do all sort of amazing things. But then you can think about trying to communicate something and just being able to on the fly convert your thoughts into a video that depicts exactly what you're thinking about. And that's one of the crazy things that Sora is going to do, is democratize the ability to make videos and just make it possible to iterate on ideas real fast, to be able to like communicate. Like you want to tell someone something, or maybe you're a parent, you want to teach your child something, right? You're a teacher, whatever. You can just write a text prompt and generate a video of it and show your child, show your students. And just like really incredible, that ability to express our thoughts in this new medium. Also, of course, it's going to provide the ability to visualize educational content. You can take about a teacher preparing for class, and you can just like generate videos on the fly to aid as a teaching aid, to make it easier for students to understand what they're trying to teach them. And I think that's like really incredible. Of course, one of the most important things that Sora is going to be used for is to generate lots and lots of multimodal data to train general purpose models, such as future GPT versions. So Sora is like a world simulator that can then be used, because it understands physics, it understands 3D, it can be used to generate lots of multimodal data, which is going to become more and more important to train like general purpose AGI models. And it will enable AI models communicate with us via text, images, and video. So right now, you could communicate with and a general purpose model via text. You could send it images. And then in the future, they'll be able to like not just communicate back to us with text and images sometimes, but also communicate back to us with video by, sharing, their outputs with us, in ways that are like really incredible. So I think like this is like an amazing time that we live in. And I'm sure before the end of the year, we are going to have so many more crazy technologies that's just going to blow our minds. And I think there's never been a more exciting time to be alive. So this is really the first in the series of videos. I'm going to be making a lot more videos on like some of the most crazy technologies out there right now, and how they work, what's their history, what's the societal impact, and just kind of get every one of us to think more about how we could contribute to this technology, how we could ensure that it is safe and used in like the most positive ways, how we could mitigate the negative aspects of it. And yeah, I think it's going to be an amazing ride, for the next couple of years as we, head towards this vision of like building AGI models that actually serve us in good ways. Thanks a lot for listening to this video, and yeah, have a great day.